Hello, everyone. Thank you for joining Control Automation Day, brought to you by EETech Media and Control.com and sponsored by Mouser Electronics. My name is Dale Wilson. I'll be your moderator for our next session. Before we jump into this session, I'd like to announce our giveaway winners from the previous MER keynote session. Congratulations to Thomas Nord and Ian Parker. You'll receive an event t-shirt and 6-in-1 multi-use screwdriver courtesy of Mouser Electronics. We'll be in touch with you after the event to ensure we have the information we need to send you your giveaway package. Now, on to our next live session, which is titled Beyond Repeatability, How Accuracy is Driving the Next Generation of Industrial Robots, and is brought to you by Mecademic Industrial Robotics. Let me tell you about our presenter. Ilian Bonev is a professor at ETS in Montreal, which ranks among Canada's foremost engineering institutions for 2 decades. His academic pursuits include teaching an undergraduate course on industrial robots, as well as conducting research in the field of precision robotics. As the Director of Control and Robotics Laboratory, Dr. Bonev oversees a facility equipped with an extensive array of industrial robots and advanced metrology tools. In 2012, alongside one of his graduate students, he co-founded Mecademic. This company is renowned for producing the smallest and most precise industrial robot arms in the market. Following the presentation, we'll have a live Q&A with Gabriel Boucher, Mecademic's calibration specialist. You can submit questions at any time during the session using the chat box on the right-hand side of your screen. We will also provide all attendees with a PDF version of the presentation near the end of the session. You'll be able to find this under the Handouts tab in the upper right. Thank you so much for joining, and with that, I'll hand it off to Ilian for the presentation.
Hello, I'm going to talk about repeatability and most importantly about accuracy, which is much better than repeatability. My name is Ilian Bonev. I've been a professor at ETS, a large engineering school, very practical, very practice-oriented, industry-oriented in Montreal for the last 2 decades. I've been head of the control and robotics lab, where we have dozens of different industrial robots, big ones, small ones. We have lots of metrology tools, CMMs, laser tracker, Renish interferometer systems, and so on. I've been a Canada Research Chair on precision robotics, and I'm also co-founder of Mecademic, manufacturer of the smallest and most compact and most accurate 6-axis and also SCARA industrial robots. So we're not going to talk about palletization. We're not going to talk about applications where you don't need precision. We're talking about precision robotics today. So just a small review of what is precision, which in industrial robotics is basically repeatability, and versus accuracy. So in precision, as you can see in this picture here, where we measure the repeatability of our Mecha 500 6-axis robot, we basically teach a given joint configuration, or if you want, position, and then we just repeat this motion over and over again. And then with this kind of tool, which is used in machine tools, which has 3 capacitive sensors, very, very accurate, we measure the difference in the XYZ direction from the initial position that we thought. And you can see here on the screen, every time we return, we basically have 2 micrometers, sometimes even 1 micrometer, up to 4 or 5 micrometers of deviation from the initial first measurement. So this is repeatability. I mean, repeatability, it's a bit more complicated. There is a formula and so on, but basically this is repeatability. Now, accuracy, it's completely different. Accuracy is when you, for example, in this case, it's a relative accuracy. You use a laser interferometer, which is basically a tool for measuring very, very precisely motion along a line. So in this case, we just measure the linear displacement along a line, and from 0 to 800 millimeters displacement on 3 different robots. And we see that some of the robots, after 800 millimeters of displacement, they have up to 2 millimeters of error, which is usual. It's not a bad robot. That's usual. Even our small robot, well, it's smaller, so it's much better, but it's still like not accurate. Like after manufacturing the robot, after manufacturing, robots are not accurate. So unless you calibrate them, we'll talk about calibration. This is normal to have as much error, and people don't know this because we always talk about precision, repeatability, and something that when we say 5 micrometers, well, that's also accuracy. But accuracy, no, it can be 5 micrometers of repeatability. But then if you tell the robot to do a motion of displacement of 1 meter or almost 1 meter, you can have 2 millimeters of error. So that's accuracy. Or in this case, we measure the distance between two balls with a Renshaw telescoping ball bar. And you can see then if you make a circle of 100 millimeters of radius, you can have up to 0.4 millimeters of deviation, plus minus, from this 100 millimeter specified radius. Now, who really needs precision? Very, very high precision, like a few micrometers precision. Well, anyone who needs repeatability of less than 0.5 millimeters. Because as we'll see, it's not because the manufacturer tells you that your Mecha 500 has a repeatability of 5 micrometers. It doesn't mean that whatever you do with your robots, it will repeat 5 micrometers. No, because if you have like plastic fingers, if you put the robot on some flimsy base, it will not repeat within 5 micrometers, of course. And then also, even if you machine your fingers, if these fingers are not exactly aligned, they will not repeat. The fingers themselves, the gripper itself, it's not 5 micrometers. So keep in mind that like when the manufacturer says it's 5 micrometers, this is kind of an ideal case. In practice, as we'll see, it can be worse than 5 micrometers. So don't tell yourself like, oh, the Mecha 500 is an overkill. I don't need 5 micrometers. You need 5 micrometers because you have different kind of errors. So maybe you will actually have like 0.1 millimeter of repeatability with your plastic fingers and so on. So if you need repeatability of less than 0.5 millimeters, buying a robot that has 10 micrometers of repeatability, that's not an overkill. Definitely, that's normal. Now, who needs accuracy? Not everybody needs accuracy, because basically accuracy, you definitely need accuracy for some application. For example, for inspection. You cannot have a 3D scanner. I've had people come to my lab and they think that because their scanner is super accurate, they can just put it on a robot and then the robot can scan something and then everything will be within the accuracy of the scanner. No, because the robot tells you it's here and then it's here, but there's a big error. It's up to 1 millimeter error. So even though your scanner is super accurate, then when you try to construct the whole 3D model, it's not accurate, right? Material removal, if you do machining, if you do deburring, finishing, whatever, but if you use a CAD model, and then from this CAD model, you offline program the robot, well, you need accuracy. Maybe you don't need like 5 micrometers of accuracy, but you definitely need a robot that is calibrated. If you have too many features that you can always teach one by one, but it's way too long. Teaching, fine-tuning, it's possible, but it's super long. Like if you have a tray with 10 by 10 parts to teach, yeah, of course you can teach them, but if you have an accurate robot, then you can just teach three positions and then interpolate between this. So you save time. So sometimes to save time, sometimes there's no other way. Swapping robots. So even though you have two robots from the same batch shipped at the same time, they will be different. You run the same program with the same XYZ coordinates, motions, they will not do the same motion. One robot will do this, the other robot will do that, and there will be like 2 millimeters of difference. But if you need accuracy, before even thinking about calibration, which I'll talk about, start by measuring your tool reference frame, because the worst, like the easiest source to correct of error is the bad measurement of your tool reference frame. So because sometimes it's really difficult to measure the tool. It's a camera, it's a 3D scanner. So how do you measure the coordinates of a 3D scanner or a camera? So sometimes you can measure it on a CMM. Sometimes you have to kind of identify it or calibrate it. But that's very, very, very important. Now, what do we have as metrology tools in robotics? In robotics, we can use almost any kind of metrology tool that is usually made for machine tools, which are generally much more accurate than robots. So you can use telescoping ball bar. It's a fairly inexpensive tool, very, very easy to use, Bluetooth device. You can use laser interferometer systems from Renshaw. You can use CMM, which is good for small robots. For big ones, kind of they don't have those huge CMM that you would need for a big robot. You can use a laser tracker, of course, especially for big robots. For ours, it's not that accurate, but you can use a laser tracker. We've used laser trackers. You can use this kind of device, which measures, it's basically called the R-test device. It measures the XYZ position of a ball, special ball. Or you can use a cheaper version of that device, which is made of 3 digital indicators kind of mounted on a fixture in an orthogonal manner. This is something I designed in DETS. You can use optical trackers, which are good because they measure in real time the XYZ coordinates and even the orientation of different objects, but they're not that accurate, especially for small robots as ours. And okay, what's the difference? Why robots are precise but not accurate, right? So precision, not every robot is precise. Like if you buy my kids when they were young, they would play with this kind of robot, and it's not accurate. It's made of plastic with very cheap gearboxes. So obviously, if you buy a robot for, let's say, I don't know, $1,000, definitely it will not be accurate. It will not be precise, let alone accurate. Precision means more expensive because you have better gearboxes. It's the gearboxes, one of the most expensive parts of a robot is the gearboxes because they need to be perfect. Zero backlash, low hysteresis, quite rigid. You also need high resolution encoders. So this is what makes a robot kind of more expensive. It's the precision. If you don't need precision, yeah, you can buy a robot for, I don't know, $2,000. But if you need precision, definitely you will not get it for $2,000. That doesn't exist. High accuracy. Is it possible to make a robot that is super accurate? Perhaps it's possible, but it will be 10 times as expensive because for high accuracy, you need perfect machining. Everything needs to be, I don't know, granite plates and then super accurate assembly, gearboxes, encoders, no deflection, like a CMM. When you make a CMM, it's everything. It's big. It's precise. But even though everything is so good, so well made, and it's so expensive, you still need calibration. Or, as in the case of robots, if somebody needs accuracy, Then we take the normal robots that we usually ship without calibration, and we do the calibration to make it more accurate. We'll talk about calibration, what this calibration is, but basically it's a kind of a measurement process and some kind of mathematics, and then the robot is more accurate. Or the best scenario is to use an external guidance. The external guidance can be a laser tracker or some kind of other metrology tool, but then of course it's super expensive, this kind of situation. So, precision. There is a norm that prescribes how precision must be measured. So precision from one manufacturer to the other, we all use kind of the same method, so it's kind of easy to compare the results. But then again, so this norm basically tells us that we have to visit 5 different points within a diagonal plane of a cube, and there is a pattern 1, 2, 3, 4, 5, and then we repeat this 5 times. And there is a given formula that we need to use, which takes into account the standard deviation and so on. And so it's quite normalized, but there are still, like, do we use the maximum payload or not? Do we, what is the TCP, the tool center point? Like, what kind of tool we use for the measurement? Is it a laser tracker, an optical tracker, or a CMM? What is the orientation of the robot when doing this at the end effector? Do we have a warm-up or not? So even though we have a norm, there is still some uncertainty about if one manufacturer does it this way and the other does it that way. But in all cases, repeatability typically refers to unidirectional repeatability. So we always come from the same direction to the point where we measure the XYZ coordinates. How do we measure repeatability in industry? Well, almost always, except in our case, we use a laser tracker, because a laser tracker it's quite accurate, especially for big robots. It's pretty accurate, very easy to use. You can automate everything, and it's contactless. So it's really the best device for larger robots. But it's not accurate enough for robots like ours, because even if you don't move the reflector, which is called the spherically mounted reflector with 3 mirrors where the laser is shot, even if you don't move it and you just move the laser tracker and then you come back, you move it away, you come back, you will still have 5 micrometers perhaps of error, and the ball hasn't even moved, right? So you cannot use a laser tracker to measure a repeatability in the range of 5 micrometers. It's kind of, it's not accurate enough. And by the way, since if you cannot use a laser tracker and you have to use this kind of device where the only way to measure it is if you come from this way, you cannot come sideways, and you can only have one device, you cannot have 5 devices of this because they are very expensive. So this makes it impossible to use the ISO norm. But the beautiful thing about repeatability is that even if you don't use the exact tests prescribed by ISO, as long as you use their formulas and you measure it here or here, it's pretty much the same. So repeatability, it's quite the same as long as you don't measure it in some, like the perfect location, whatever that is. It's pretty much the same. So it's kind of difficult to cheat if you want. It's even if you don't use the norm, as long as you use 30 repetitions and you use the same formulas, it gives pretty much the same results. As you can see here, like all these 5 points, they're very, very different. One is here, one is here, 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 and here. And we don't use the exact norm for this measurement that I made in my lab, because again, you're supposed to go from P1 to P2 in a straight line. But with this kind of device, you cannot. You have to, retreat and then come to the P2 and then approach P2. So, but even with this way, we kind of get the same results as the ones specified by the manufacturer. And as you can see, P1 or P5 or P3, it's pretty much the same repeatability. It's between 9 and 12 micrometers. So where you measure the repeatability doesn't matter that much. Now, what matters and what you should understand, and this is why I was telling you that it's not because the robot has 10 micrometers of repeatability, or 5 in our case, that it will always be this way. Here's the demonstration. So basically, when you do this test, you come once and then you come 30 times, but it's always in the same direction and it's the same. Everything is the same speed, everything is the same. But in practice, this is not the way you program robots. You kind of program a robot by going slowly left and right, and then you stop somewhere. And then, I don't know, 5 hours later, you start production, and then you start going here over and over again. And so when you taught this position, the robot was cold. And then when you started repeating this for 5 hours, well, the robot got eventually warmed up. And you can see that after a couple of hours, you can have up to 0.3 millimeters of error from the initial state, which was your, teaching moment, till like five hours later. And this is only five hours. Imagine if you do this for 5 months. Obviously, it will not be 5 micrometers from the position that you taught 5 months ago. Okay, so this is why, again, it's not because the robot has 5 micrometers that for 5 months you will repeat it 5 micrometers repeatability from the location which you taught 5 months ago. So don't think that 5 micrometers is an overkill. It's not. Now, this is about accuracy. This is about repeatability. Now, what's accuracy? Accuracy, we saw what's accuracy, but why robots are not accurate? Well, because when we manufacture them, the distances between the axes, the angles, they're not perfect. During the machining, during the assembly, when we insert the gears or the bearings, it's from one robot to the other, there are always small errors. And these errors accumulate, and then the actual robot is different from the perfect robot, which is modeled in the controller of the robot. There is a test of how to measure accuracy in the ISO norm, but that's not good, because accuracy, unlike repeatability, it's kind of random, especially after calibration, right? So the only way to catch the actual accuracy of a robot is to do as many measurements as possible, because if you only measure in 1 or 2 or 3, you can be lucky and the error can be very small. But if you measure it 7,000 times, you will see that the data is quite different. So fortunately, nobody uses this norm, and manufacturers basically, they will validate the accuracy in 20 or 30 or 38 or 100 different random, maybe not completely random, but kind of almost random configurations. This is the way manufacturers measure the accuracy of the robot. Because once again, for CMM machine, for machine tools, we have a very good norm for how to measure accuracy. For robots, the norm for measuring accuracy, I mean the specification for measuring accuracy is not good. So there's no way to compare from one manufacturer to the other. That's one thing. And also it depends how many measurements you do. Like when you're in a lab, like me, your students, they have 3 years to complete their PhD, they have plenty of time. So they will take thousands of measurements with the laser tracker. And this is what looks like if you take many measurements. Before calibration is the blue histogram. So you have up to 1.8 millimeters and most measurements are below 1 millimeter, but still it's like about 1 millimeter error. And after calibration, which I haven't yet described, I haven't introduced what calibration is. We'll talk about this. And so after calibration, you get the worst case scenario is 1 millimeter. But then again, maybe if I continue to measure, I will still have some outliers, but most of them, they will be below 1 millimeter. So again, I have no guarantee that I will never, ever have more than 1 millimeter of error, but most of them are much better than 1 millimeter. So it's not like repeatability. Again, repeatability, if you measure here or here, it's pretty much the same. Accuracy is very, very different. It's kind of random. You cannot say, especially after calibration, you cannot say, oh, the robot is more accurate here than here. It's kind of random. You can say that the robot, if it makes a small displacement, whether after calibration or before, for a small displacement, the relative error will be very small. But if you measure the error with respect to the base of the robot, so kind of an absolute accuracy, then it's kind of random. Here it will be very good. 5 centimeters away, it will be worse, much worse. It's kind of random, especially after calibration. Okay, what is calibration? So calibration is basically we develop a more sophisticated model, usually more sophisticated. It can be the same model, but usually it's more sophisticated, like some distances which were considered to be zero now are no longer considered zero, and because of this, the model is kind of more difficult. The inverse kinematics is more difficult, and so on. We can even consider that the stiffness of the joints, instead of being perfect, now it's kind of flexible. The joints are flexible, so we have to identify the flexibility. And then we do lots of measurements of the end effector, the position and orientation of the end effector, using a laser tracker or some other tool, in our case a CMM machine, because it's much more accurate than a laser tracker, and our robot is very small, so why use a laser tracker? And by the way, a CMM is even more affordable than a laser tracker, so it makes no sense to use a laser tracker in our case. And then you kind of run optimization methods and try to find the values of the parameters of your model that kind of make the errors in the position and orientation where you did your measurements, the errors are smaller, right? So you have no guarantee that the errors will be smaller in random robot configurations. But of course, if they're smaller in these 100 or 50 measurements, we kind of expect that they will be smaller elsewhere as well. So you have to, so this set of parameters that you have kind of identified, this is called the robot signature. If the manufacturer does the calibration, this robot signature is kind of inside the controller, and then the controller, basically it's transparent. The user doesn't see the difference. The robot, when you tell the robot to do a 1 centimeter displacement, well, after calibration, this 1 centimeter displacement will be much more accurate than before calibration. And when we send the robot to a client who had ordered the option of calibration, we do validation to make sure that the robot is more accurate in random other poses, not only in the poses where we used for the calibration. So ideally, we should use as many as possible, but of course, it takes time, especially with a CMM, it's very, very slow compared to a laser tracker. So we cannot measure thousands of different configurations, but we measure 100 or 50 random additional measurements. And then we specify this and give this to the user, to the client. And again, we don't have any guarantee that the robot will not be, the accuracy will not be worse somewhere else in the workspace of the robot. But we have a very good assurance that most of the errors will be below this and that value. So, and by the way, calibration does not improve path accuracy. When you do a move L, like a move lane, trajectory between two poses, continuous movement. So this movement will not be better than before. It's the final destination that will be reached with more accuracy. But the movement itself, during the movement, we will not use the new sophisticated model because otherwise it will take too much calculation power to do this. It's possible, but we don't do it. Nobody does it. And by the way, mastering, what we call mastering, is kind of a simplistic calibration where we identify only the offsets of the actuated joints. So we talked about like taking measurements. How many of them? Like if you calibrate your robots at a manufacturer, they will give you maybe 50 or 36 measures. So the mean value is quite good, an estimate. Standard deviation as well. But of course, the maximum, don't expect that the maximum will not be worse. Because if you do 7,000 measurements, well, in this case, it's our own calibration, so it's not exactly the same calibration as Fanuc did on our robot. But if you do our own calibration, then the mean value is even better than from what the manufacturer states. The standard deviation is a little bit worse, but then of course the maximum is worse because you can see you have very, very few, but you still have poses, configurations where the error is up to 0.9 millimeters. Most of them are less than 0.3, but there is no guarantee that sometimes it will not be 0.8. So this is something you should know. Even though the manufacturer, like in our case, Mecademic, will tell, oh, the maximum is 0.2 after calibration. Well, we have no guarantee. Like if we take 1,000 measurements, maybe sometimes it will be 0.5 millimeters. But in most of the cases, it will be much better than 0.2 millimeters. So there is no guarantee, but generally it will be better. So accuracy, calibration, you cannot blindly rely on this, but it's the best you can expect. There is nothing best than calibration. And so if you are swapping the robot, maybe you need to fine-tune a little bit the program. If you are doing something else, maybe you still need to do the fine-tuning, but this fine-tuning will be much less than in the case of a non-calibrated robot. So for sure with calibration you win. It's not perfect, but you definitely win with respect to a non-calibrated robot. Now, we talked about calibration being done at the manufacturer. This is the best because it's kind of transparent for the user. But you can also use like a third party, like Robotic, which was developed by a student of mine. Robotic, they calibrate some of our robots, and they do a very, very good job. The only problem is that you have to use their software all the time, because the new model is not inside the controller of the robot, it's inside Robotic or Dynalog or whatever software you use for the calibration. So you need what is called the post-processing. It's more expensive, especially if you do it only for one robot, it's more expensive. Maybe if you do it for many, many robots, it's better to do it at to buy your own software and then do it yourself. But then again, you have to buy a laser tracker, so it's almost never less expensive to do it yourself, but it's more flexible, because let's say you have a very, very special tool, well, you can use the exact tool you use, whereas we, the manufacturer, we kind of use no tool or always the same tool, and we cannot easily adapt our process for your very, very specific application, whereas instead of a soldering tool, you have a camera or something else. So that's the disadvantage of doing the calibration at a manufacturer, is that it's kind of generic solution. But if you have a very, very particular case where, let's say, you don't move everywhere, you only move in a small volume, then maybe if you only have one robot to calibrate, maybe we will not do it. The manufacturer will not do it because they are set up for this kind of process. And then if you want to have a very, very different process, then it will have to be customized and so on. And then the best accuracy is achieved when you use, well, not the best, but much better is when you use secondary absolute encoders, but then you cannot use secondary absolute encoders on small robots. This is only for very, very big robots. And even if you use absolute encoders, you still need calibration. But the best case scenario is when you use an external metrology equipment. But then again, for big robots, that's great because you can use optical trackers, laser trackers, but for small robots like ours, you cannot use it. So the only way to improve small robots is through calibration. So thank you very much. I hope you some kind of got an introduction into calibration, accuracy, and precision. And if you have any questions, I will be happy to answer you. Thank you.
All right. Thanks, Ilian, for that great presentation. We already have several good questions in our queue, but there is still time to submit your questions. So if you have some, put those in the Q&A section in the right-hand chat box. And as I noted before we started, we're now being joined by Gabriel Boucher, Mecademic's calibration specialist. Gabriel, are you ready to answer some of these questions?
Yes, sure.
All right, well, let's jump to the first one. And this is an interesting one to me, too. I was wondering about it as I was watching the presentation is, what about resolution? Is this similar to repeatability?
Yes, so the resolution is one of it's like the third, I'd say, parameter of robots. And we hear about resolution when we talk about cameras, about sensors, things like that. But it also exists with robots, right? But the resolution is essentially just the smallest possible movement that the robot can do. Generally, this is going to be slightly better than the repeatability. So, for instance, in our robot, the repeatability is 5 microns, but the resolution, we have customers that use it down to even 1 micron of steps. So if you're using, and Ilian talked about this a bit in his presentation, if you're using external metrology systems, it could be camera, it could be a laser tracker, something like that, you can adjust the position in real time using the resolution.
Okay, thank you. Our next question is asking about in the offline programming scenario where compensation after calibration is done virtually. In this way, is there any possible approach to compensate a real robot with a corrected model? And they propose like a parallel controller, maybe? And I'm not sure I'm following that question.
So this might be referring to when Ilian talked about the path accuracy and things like that. So generally, when using an external controller and the calibration, let's say you use RoboDK and you do your calibration externally, and then the model of the robot is on an external controller. I mean, you can do some kind of compensation if you basically break off your path into very, very small increments. You can still get some pretty good accuracy on the path itself. There's also ways to do, sometimes we've seen active compensation for some things like welding and painting for bigger robots usually, where you have some kind of sensor mounted on the robot and then you can do active compensation like that to correct some path. In our case, I'd say, like Ilian mentioned, that the path accuracy is not better. In our case, it's not completely true because we do use the full model inside the robot when we calculate, for instance, a straight line. So the path accuracy might not be as good as the normal accurate, like the static accuracy, just because there's a lot of dynamic movements and like vibrations and things like that. But it's going to be better than a non-calibrated robot.
Okay, interesting. This question is, how often do you need to recalibrate your robot?
So that's a good question, especially for people running production. You want to know like when do you have to take it off, get it recalibrated. The answer is it mostly depends on how you use the robot. Generally, you don't really need because unless the robot physically changes, the calibration is going to stay the same. So unless you notice a loss of repeatability, a loss of, and you can do tests like if you can have some, for instance, a golden position that we can call maybe that where you go back and you test a few different movements to see, okay, are my movements still good? Do I need to recalibrate the robot? But as long as the robot doesn't lose any repeatability, which is uh, very rare unless like you have wear and tear in the gearboxes and things like that, you don't necessarily need to recalibrate the robot. Where you might need to do a recalibration is if, for instance, you're changing, let's say you calibrated with a tool mounted on the robot, and you need to recalibrate, you need to change the tool and you want the whole system to be calibrated, then yes, you're going to need to recalibrate it. But the base calibration of the robot doesn't really need to be redone unless there's been some kind of change in the robot itself. Maybe the robot hit something and there's been a little like movement in the assembly or something like that. But that's pretty much it.
And so, just kind of playing off of that question, then adding things like sensors for looking for acceleration. So if you had something like you hit something that was out of what you're expecting, or you're taking sensor data that's telling you something, it'd be a way to incorporate that to help you predict when you need to do a calibration.
Yes, exactly. So if you usually, and that's true for any, like for instance, we have our CMM. So we have, let's say somebody from the company comes and calibrate our CMM. We're gonna have, for instance, a golden part that we use that we measure, and then every, I don't know, few weeks, every month, we remeasure that part and make sure that like the CMM gives the same result. And if the CMM gives the same result, we're good. We don't need calibration. The same can be done with the robot. If your robot um, does come back to the exact same position all the time and you can measure that, you don't need to recalibrate it. The math is the same and the actual position is the same, so you're good to go.
And you just mentioned the golden part, which kind of goes into this other question here: is how accurate does your calibration standard need to be relative to the measurement you're making? And then do you need to periodically calibrate your calibration standard?
Yeah, so that's also a good question. So obviously, yeah, we get our systems calibrated before every so often. There's no longer any like standard that every year you need to calibrate your CMM or things like that. But yes, we need to have to make sure that what we use to measure is at is good, and measure the proper thing. As for what the scale should be versus what you're trying to measure, as Ilian showed, like the accuracy of robots is usually much worse than the repeatability. So if you can get a measuring tool that is about the same as your repeatability, even it could even be a bit worse. It's going to be fine. But generally, you want it to be like more precise than what you're trying to measure. So in our case, I think our CMM is down to 1 micron of accuracy. So since our robot is 5 micron repeatability, we can rely on the CMM to be precise enough or accurate enough.
Excellent. This question asks, can you also calibrate a SCARA robot?
Well, if you ask if we can calibrate our own SCAR robot, currently no, because we haven't developed the process for that yet. It's a new product. But if you ask in general, can you calibrate a SCAR robot? It is doable, absolutely. It's a different mathematical model. It's a bit of a different way to measure, but at the end of the day, it's just having the right model, taking the measurements, and then finding the right parameters. And it's something that we're going to investigate depending on the if our customers need it or if we have a request for it.
Okay. Well, that's a fun question. Can I mount a calibrated robot in any orientation?
Yes, that's a good question, especially considering that our robot can be mounted in any orientation, and this is true with a good amount of robot out there. The answer is really dependent on how the calibration was done. In our case, because we don't, for instance, use the stiffness model in our robot necessarily, um, if you calibrate your robot upside, like right side up, you're going to have some kind of influence from gravity on your robot. Even if the robot is very small, there is still some kind of there's still some force applied by gravity. So if you flip the robot upside down when you actually use it, that force is on the other in the other direction. So you're going to have a basically worse outcome when it comes to accuracy, because all the flex in the joints, even if it's very small, is going to be uh, completely the opposite of when you calibrate it. So you can use it at a different orientation, but you're not going to get the same results. That's for sure.
This question asks, why can't you calibrate a robot to be as accurate as its repeatability?
This comes from it's a very good question. So the reason why is mainly just a limitation of how the process is done. We use an optimization technique that is very basic. If you could take an infinite number of measurements, you could probably find the actual values of the mathematical model. But even then, your model is never going to be perfect unless you can perfectly model a robot, which is like not possible. There's temperature taken into account, there's deformation of the gearbox, hysteresis, backlash, all those things. If you could build a perfect physical model of the robot, you could have the same accuracy as the repeatability, but this is just completely unrealistic for a real robot in any case. So the best you can do is generally like get like maybe one like in our case it's 5 micron of repeatability, we get to 100 micron of accuracy. In local calibration, we have customer that went down to around 30 micron, but that's for a very small workspace and not the complete workspace of the robot. So even then, that means that it's going to be very accurate in that small workspace, but as soon as you go outside of that, you change completely configuration, you're going to be way off because the model doesn't fit at all.
Yeah, and you mentioned something interesting there. There's, as the temperature changes and as the tool wears over time, that you're going to have a different performance constantly to some extent.
Yes, exactly. So for instance, when we do our calibration, we make sure to warm up the robot so that it gets to a temperature that is somewhat stable and also ideally fairly representative of what's going to be happening in a real application. But of course, if I calibrate a robot and it's at like, I don't know, 30 degrees, and it's all nice and warm, and then you take it out of the box, you start testing, and the robot is cold because it's just came back from the plane, you're going to have different results. So you need to make sure to do the warm up and use it at the ideally same temperature. As Ilian said, this is there's never any guarantee of accuracy when it comes to calibration. It's going to be much better. It's almost always going to be better than what you had before. But there's so many variables that can play around with the accuracy that it's hard to really make sure that it is perfect.
Well, it looks like we've covered all of our audience questions. I will let everyone know that the handouts are available. So if you want the slide deck, go up to that handouts tab in the upper right corner. You can download those files. Thank you, Gabriel, for joining us in the Q&A.
My pleasure.
And thanks again to Ilian for his great presentation. Before we wrap up, I'd like to announce our giveaway winners for this session. 2 winners will receive an event t-shirt and 6-in-1 multi-use screwdriver, courtesy of Mouser Electronics. Congratulations, Mark Epperson and Samuel Todman. We'll be in touch with you after the event to ensure we have the information we need to send you those giveaway packages. And thank you for attending Control Automation Day 2024. In a moment, you will be redirected to the event landing page. I encourage you to check out the Mecademic exhibitor booth, as well as today's other live sessions, keynotes, and published content. Thank you.